Hello everybody, welcome to chapter 3 of particle and nuclear physics. Today we're going to be discussing colliders and detectors just to set the scene of how we actually do a lot of the collider physics that we'll be discussing in the rest of the course. And what we have here as a picture is my detector, the Atlas detector. As it was being built. Here we have these massive toroidal magnets. This is about 45 meters long, these massive toroidal magnets that provide a magnetic field in the outer parts of our detector. And since this photo was taken, this entire space here has been filled with tracking detectors and calorimetry that I will be showing you today. So we'll be talking about the physics of colliders. You need to know how they actually work and how we're doing our particle investigations and the different types of detectors that we can have and how we piece these all together to detect and identify particles that are coming out from collisions. So we've been talking about this center of mass energy or this invariant mass, and this is very important when we're colliding two particles on scattering them in the hope that we're going to make something new and interesting. So let's consider this situation where we've got two beams of particles, i.e. two particles coming in to collide head on at this point here. What we're interested in is that invariant mass, that invariant quantity of this system of particles, that center of mass energy. So we can sometimes call that S or ECM squared, and it's the sum of these two 4 vectors of particle 1 and particle 2. So when you take the sum of these two 4 vectors, you need to sum their energies and square that, and from that subtract the sum of the momenta squared. So we did this in the previous lecture, but it's good to go over it again because this is something you'll need to be very familiar with. So you sum their energies and square it and subtract the sum of the momenta squared. And then we have terms that look like the mass of particle 1 with its energy squared minus its momentum squared, and the same for particle 2 here, the energy squared minus the momenta squared. So we can write that as the mass of 1 squared plus the mass of 2 squared. And then we have the terms that are the product of the two energies and also the product of the two momenta, which we can write as the magnitude of their vectors and the angle between them. So this center of mass energy is really important. It is the invariant mass. It's something that's invariant on whatever frame of reference you're using, but it's the amount of energy that we have to create something new in the collision. So if we're going to have these two particles, for example, an electron and a positron, they could annihilate, and it's the maximum energy or mass of the particle that we can produce. So that if we're interested in making something heavy and interesting and new, for example, the Higgs, we better get quite high center of mass energies so that we can achieve that. So there's two types of collisions, scattering experiments that we could do. We first started with fixed target collisions. So taking a beam of high energy particles and targeting a fixed target. So maybe a thin foil or a block of lead to see what comes out. Now here, one of your particles in the collision is at rest and the other one is moving. So the one that's at rest, its energy is simply its mass and its momentum is 0. The one that's moving has both energy and momentum. So when we have a look at our center of mass energy here, or S, we will have you can see it from the previous slide here, we'll have the mass of the first one squared, the mass of the second one squared, but that those don't change. But then since the magnitude of that second vector is 0, then we'll just have plus 2e1, e2. So that's what we've got here too. And this e2, of course, is just m2 because its energy is just its mass. It has no kinetic energy. So this is, we can simplify this a little bit more. So if we're aiming very high energy particles, at others. Maybe we've got some 500 GeV electron beam here that we're firing at um, some target. That energy is going to be far higher than the mass of the electron here, or the masses of the protons, or whatever it's aiming for in there. So we can simplify this a bit and call it an ultra-relativistic scenario and treat these two particles as massless. So when we do that, these two terms disappear, and our center of mass energy squared here is just 2e1m2. So our center of mass energy is square root of s here. You just square root that. So for example, if we had a beam of protons here, 450 GeV in energy, that's very high energy, much higher than the mass of a proton, which is about 1 GeV. We can have this hitting a proton at rest in our target, whatever we've got here, lead, whatever. Then our center of mass energy here is going to be 30 GeV, and that's the energy that we have to create something new. So we can create new particles up to 30 GeV in mass, which isn't particularly exciting. Now, let's have a look at the collider experiment where we have two beams colliding with each other. This is slightly harder in terms of the accelerator science, because you have to get those two tiny beams, which are about the width of a human hair, to collide head on, usually over, for example, in the LHC, over the sort of distance of kilometers. So it is very hard, but it's something that we can do really well. So now both of our colliding particles have some momentum. We could, for example, have them with equal and opposite momentum. And our center of mass energy squared here is just simply the equation that we had on the previous slide. This term has not gone to zero because the particle 2 has some momentum. So let's pop ourselves into the ultra-relativistic regime where the energy of our beams or our particles is much higher than their rest mass energies. So their momentums are roughly their energies, and we can treat their masses as roughly zero. We're also going to collide these two particles head on, so with an angle of pi. They're really colliding with equal and opposite momentum. So our center of mass energy there then simply equates to 2 times the energy of our beams. So if we have a couple of beams of protons, each with 450 GeV of energy, our center of mass energy is simply 900 GeV. And this is a huge difference with respect to the fixed target collision. So with the fixed target collision we had in this example here, we had a beam of protons and we're firing at some other protons. This beam is 450 GeV, but we can only make something of 30 GeV. Instead, if we collide two beams with equal and opposite energy of 450 GeV, now we can make something of 900 GeV. That's 30 times larger just by giving both of the beams some momentum. So what's happening here? Why are these so different? In the fixed target collision, your total momentum here of this system is not zero. There is some forward momentum from this moving particle. We can't get round momentum conservation. Our final state that we create, this particle that we create, must conserve momentum, so must go off with 450 GeV in this case of momentum. That's a lot of waste. So a lot of this energy that's available, the energy that we're putting into this beam, is actually wasted giving this new particle that we want to create some momentum. Whereas in the collider experiment, our total momentum here is zero because we have two 450 GeV beams cancelling each other out. So none of the energy then needs to be wasted in giving the final state any momentum. It can all go in to create the mass of the particle that we're trying to make. So this is why these days we do collider experiments rather than fixed target collisions. We are trying to access higher mass, exciting new particles that we haven't seen before, and the most efficient way to do this is by colliding two beams head on. So let's have a look at this. We know we need high center of mass energies to create the new exciting particles that we want to create. How do we do that? How do we get these beams to high energies? We use radio frequency high voltage cavities to accelerate our particles. So it's a simple drift tube where we are turning the frequency on and off and accelerating our beam to higher and higher energies through these drift tubes. It's really that simple. And there's some energy gained um, depending on the electric field that you're applying across these drift tubes. So the higher the voltage you're applying, the higher the energy gain. But the problem is that this is sort of space, it's limited by space because you're going to need longer and longer and longer distances of drift tubes to accelerate your particles up to higher energies. So for example, we had SLAC. I'm just going to switch what I'm showing. We had SLAC, which was a collider out in California, in Stanford, in San Francisco, which was a LINAC, so it was called SLAC. So that had RF cavities, these radio frequency cavities, and they were state of the art at the time. And they provided an energy gain per length of 50 GeV over a 3.2 kilometer complex. So there was 3 kilometers of drift tubes. That's very, very long. And over that distance, they could accelerate electrons or positrons up to 50 GeV. And so here, that means that they were gaining 16 GeV per kilometer. Now, our accelerated technology has moved on a little bit, but things aren't orders of magnitude different. So if we wanted to do something at higher energies, instead of 50 GeV electrons, let's say we wanted to collide 7 TeV electrons. If we used the same detector technology here, the distance that we would need would be 7,000 GeV, and they'd pick up 16 GeV per kilometer. We would need 440 kilometers worth of drift tubes. So this doesn't scale up very well when we want to do very high energy collisions. Let's switch back and it'd be good if I could do this quicker. Let's switch back. There we go. So linear colliders were how we started doing these things, but as we want to push and push to higher energies, it doesn't scale up very well. We don't have 440 kilometers of land to be able to accelerate electrons up to 7 TeV. Right, so instead what we do is we use these accelerating cavities in the same way, but instead we bend them in a circular path so that we can continue accelerating these particles around and around and around to higher and higher energies, essentially reusing our radio frequency cavities, which is really cool. Now, we can't use the entire ring to accelerate these particles. To make them go into a curved path, we need to include magnets. So we're going to bend them around this circular path using magnets. And we actually need very high power magnets to bend these very high momentum particles. The magnetic strength, magnetic field strength that we need is proportional to the momentum of the particles we're bending and inversely proportional to the radius of the ring. So if you build a nice big ring, your magnets don't have to be quite so strong. And let's have a look at a quick example here. This is where I miss my blackboard. Here we go. So let's have a look at a magnet situation, for example, at the LHC, which is a circular collider. We hope to, at some point, accelerate protons at energies of 7 TeV. Energy and momentum are roughly equal there because proton mass is only 1 GeV, so in a ultra-relativistic regime. Now we're using the old LEP ring here, which has a radius of 4.3 kilometers. So what magnetic field strength do we need? Let's have a look. We know it's 7,000 GeV over 0.3 times 4.3 kilometers times 1,000 there, 4 meters. And we need 5.4 Tesla for our magnetic field. That's absolutely huge. Remember that the Earth is roughly, the Earth's magnetic field is roughly micro Tesla. So this is an absolutely huge magnetic field that we're going to need to apply over this whole ring. However, there's physical limitations. We can't have our entire ring as bending magnets. We do need to have some of it as radio frequency cavities to accelerate them. Remember, that's what we're trying to do at the end of the day. So at the LHC, we've got roughly 60% of the ring is magnets and about 40% is accelerating cavities. So that means that we're going to need a magnetic field of even higher, 8.4 Tesla. 8.4 Tesla. That's absolutely huge. But it's something that we can achieve with superconducting magnets. I do urge you to go and have a look at the technology that we're using. It's absolutely fantastic. They're cooled by liquid helium. And after a few hiccups of when we first turned things on with a helium, with a magnet quench and helium going all over the place, we've sorted those out and they're fantastic and they're working really well. But you can imagine if we wanted to use the LHC to accelerate particles to even higher energies, we would need more powerful magnets. There's a limitation when we accelerate particles in a ring. We're limited by something called synchrotron radiation. Now, when any charged particle travels in a curved path, it will emit radiation. It will emit photons, and that's actually a power loss. If an electron, you're trying to get it maybe to 7 TeV of momentum, and it's emitting photons and slowing down, it's radiating power. It's fighting you, essentially. So we have this thing called synchrotron radiation, and sometimes it's useful. It can be useful for some things, but not when we're trying to get very high energy particles. And for synchrotron radiation, you have some radiated power. There's P, power. That is equal to the energy of the particle to the power of 4 over the mass of the particle to the power of 4 and the radius over which you're accelerating these. So we have a fixed radius collider. There's not much that we can do about that. We're trying to build at CERN, we're trying to push forward for the future, a 100-kilometer circumference collider, which will be absolutely fantastic and limit this radiation power loss. But we don't have that right now. We have a 4.3-kilometer radius collider, and that is fixed. Now, if we want to do very high energy very high energy collisions, this means that our radiated power from synchrotron radiation is really high. And we cannot get electrons up to sort of 7 TeV with the LHC collider. And that's simply because of synchrotron power. But there's this other thing here that we should have a look at, the mass of the particles that we're colliding. This 1 over the mass to the power of 4 is really important because it means lighter particles will radiate more synchrotron radiation and suffer more power loss, but heavier particles will not. And so this is why we collide protons at CERN. If you consider the power loss here for electrons over the power loss for protons, let's make this clear, electrons versus protons, and then we're going to accelerate them to the same energies. So the energy will cancel out in the same ring, the radius will cancel out. This is going to be the mass of the proton to the power of 4 over the mass of the electron to the power of 4. The proton is about 1 GeV. The electron is half an MeV. And then we're taking these to the power of 4. So there's a factor of 10 to the 13 reduction in power loss for protons. So electrons, let's say to radiating synchrotron radiation, will radiate 10 to the 13 more synchrotron radiation than protons. So protons are our particle of choice for very high energy colliders. They don't radiate. They don't suffer this power loss that electrons do, and instead we can get them up to 7 TeV. So that's why we're using protons for our colliders. Is this working nicely? Good. Right. Right, so once we've collided particles, hopefully something interesting happens. But we need to have a look at what comes out of our collisions. So around the collision point, we build layers of detectors. There's two main types of technology that we use. It's really that simple. The first type are trackers. Now, they detect ionization losses from charged particles. So they will only see charged particles and not neutral particles. We can use multi-wire proportional chambers. So as a charged particle travels through, it will ionize the gas in here, which will drift across to the wires to be read out here. And there's our signal. Or we could use cloud chambers. I think hopefully you've seen the one that's upstairs, uh, upstairs in the just by the pippard. And you can gaze at that for a long time, but you're seeing the ionization or the bubbles forming from particles as they're traveling through that gas. So the ionization loss is given by the Bethe-Bloch formula. It's very, very straightforward. The equation isn't, but it's a very, very well understood interaction that's happening there. The ionization loss itself depends only on the particle's charge, how fast it's traveling, but not on the mass of the particle itself. So we can have a look at the ionization loss against the momentum of the particles that travel through here, and it's a bit small, but particles can be quite easily identified by this ionization loss. So muons will appear down here, and taus here, kaons and protons. They all look a little bit different. So we can use the ionization loss that we measure and the momentum that we measure to identify particles when they leave a track through here. Now, when I said we can measure the momentum, that's really important. How do we measure the momentum? What we do is we put our tracking systems within a magnetic field, for example, encased in a solenoid. That provides a magnetic field within the tracker and bends the charged particles. If it bends the particles, it will bend them according to, in proportion with their momentum. And the curvature that we see, we can measure that and measure the momentum. A lot of people like to know the details of this. So essentially what we see in our tracking systems are these sort of points here that are read out by our multi-wire proportional chambers, something like that. And we get sort of hits in our tracking system. You can think about it as punching through the leaves of a book. And we can join these up essentially and draw ourselves a track for where we believe the trajectory of the charged particle went. Now we only see a portion of that that curvature, and the more of it we can measure, the better. So what we actually measure is this portion of our curved track, this arc, and we can measure the sagitta from this track arc, and this leads us to our radius because this is related to the length of our arc and also this sagitta. Now the momentum can then be taken from this radius that we measure, and we can understand our uncertainty in our momentum as the uncertainty in our sagitta over the sagitta. So what does this mean? This means that the more of the track we see, the more of this curvature we see in our tracking systems, the better we can measure its momentum. So think about a very low momentum track. It's very easy to bend in a magnetic field. It will bend a lot and have a very small radius of curvature. A very high momentum particle won't be bent very much at all by the magnetic field and will appear almost like a curved almost like a straight line. And it's very difficult to accurately measure that curvature of an almost straight line and get a good hold on its momentum. So that very high momentum particles will have a very high uncertainty on their momentum measurement. And low momentum particles, we will actually be able to measure more accurately. So this uncertainty, this resolution in the momentum measurement is proportional to the momentum of the particle itself. The higher the momentum of the particle, the larger the relative fraction of the uncertainty is. And you can have a go at this in your problem sheets and compare a couple of different scenarios for different momenta there. Okay, the second type of technology. So after being able to detect the charged particles, what we want to be able to do is stop particles and measure their energies. And we can do this for neutral and charged particles. So what we have here are calorimetry. They're well named. It essentially measures their energy, their calories. So what we do is we layer different materials of absorber to try and initiate interactions, and then a scintillator to measure what comes out. So, for example, what we have here, we have an electron traveling through the layers of our calorimetry. This very high density material interacts with the particle and initiates what we call an electromagnetic shower. Electromagnetic because it's an electron um, giving off a photon, for example, and then giving off another photon, and this photon is exchanged with the nuclei in this very high energy absorber. So it initiates this shower of lower energy particles, which we can then detect in our scintillator. And we have lots and lots of different layers of this, so we can really slow down, stop our particles, and measure these very complex showers, total them up to see the particle's energy. So whether we have these electromagnetic calorimeters, they target electrons, positrons, and photons. So whether it's a photon or electron traveling through, they're exchanging photons with the nuclei in the materials. It's very, very dense, so that happens quite a lot. And when we have more and more particles in the final state. Now, we can do the same for hadrons as well. So protons and neutrons, pions, kaons, all of these bound states of quarks. However, they have a much longer interaction length than electrons and photons. They're harder to stop, essentially. And we need to build more layers of denser material to really stop and measure hadrons. So we use higher density absorbers there and more layers out and out so that we can really stop them. They've basically got more punchability and they need more material to stop them. So it just needs more layers of there. But the calorimeters are pretty straightforward. The idea is to initiate a shower and measure the energy of the particles in those showers. So this the accuracy with which we do these energy measurements is actually flipped on its head with respect to the tracking systems. So if you think about a very high energy electron coming in here, it's actually going to produce a lot of a high number of particles in its shower. That means we've got more particles to measure, which means that we can do it with higher accuracy. It's basically a counting experiment. You're measuring a little hit from each one of these particles. If you've got more of them, your uncertainty goes down. So your uncertainty on some number count, hopefully you know this, is just the square root of the number of the particles you count. So that if you're having a look at your fractional uncertainty, which is going to be square root of n over n, i.e. 1 over the square root of n, that will go down as you count more and more particles. So the idea is that these high energy particles, as they come through, produce showers with lots and lots of particles to measure, and our uncertainty actually goes down because we can measure them with high energy. I usually just write this stuff down. So let me just change what I'm doing here. Right. Okay, so if we do some count of n, our uncertainty on n is the square root of n, And our fractional uncertainty, so that's the uncertainty on n over n, is the square root of n over n, which is 1 over the square root of n. Right, hopefully you're happy with that. It's the same thing with our particles. If the number of particles that we get to measure is proportional to the energy of the particle that's being stopped. So higher energy particles will produce more particles to measure in their shower. So that the uncertainty on the energy is proportional to the uncertainty on the number that we count. So that if we want to have a look at our fractional uncertainty in the energy, this is equal to the square root of n over E, which is then going to be proportional. Sorry, that's not equal, proportional. And then we've just got 1 over E. So we will be able to measure high energy particles more accurately than low energy particles. And that's flipped on its head from the tracking system. So calorimetry is very good for high energy particles, and tracking is very good for low momentum charge particles. Let's go back to the lecture. And again, you can play with this in a short question in your problem sheet. So how do we put all these detector technologies together to build something like the Atlas detector? And here we have a schematic, a very low-level schematic of our Atlas detector. So our Atlas detector is like a huge barrel around the collision point, and then this is just a cutaway segment that we have here. So this is our beam pipe, where our proton beams are coming in and out of the page and colliding at this point. Hopefully something interesting is happening. Lots and lots of things fly out. And around this point, we build layers of our detector technology. So the first thing we do is build layers of tracking system. That's these yellow lines that you can see down here and this green part here. These are going to detect sort of hits as charged particles travel through, and we've built a solenoid around them so that it can bend those charged particles. Then what we do is we've got our electromagnetic calorimeter here and our hadronic calorimeter here. So our electromagnetic calorimeter can stop and measure photons and electrons and positrons. And then we've got another long lot of layers of hadronic calorimetry to stop and measure those protons and neutrons, all those hadrons that have a longer interaction length. And then finally, muons, those heavier versions of electrons, are actually really, really penetrating. They are particles which can survive through the tracking system, through the calorimetry, and go into the sort of bedrock around our experiment. So what we do is we build tracking systems just here to detect charged particles like muons that survive this long. So let's have a look at what these look like. Our muon, as you can see here, what we will see is a track as it travels through our tracker. It will leave tiny, tiny deposits in our calorimetry, and then we'll see tracks in the outer layer. So that's a sort of calling card of these muons. Let's have a look at electrons. We've got one here. It's charged, so it's going to leave a track. I hope you can see this actually. It's going to leave a track as it travels through our detector, our tracking system. And then as it gets to our calorimetry, it'll initiate a shower here, and you can see the sort of like flared out shower as it's stopped and its energy is measured. A photon is very similar, but it's neutral. So it doesn't leave a track here. There's a dotted line here, but really we have no idea. We just simply see a shower in the calorimetry. So electrons and photons can be distinguished from one another from from seeing a track or the absence of a track pointing to that cluster. Right, and then protons look very like electrons actually, but make it out. They're charged, so they leave a track, and they make it out to our hadronic calorimeter and leave a shower there. Similarly for neutrons, but there's no track because they're neutral. Finally, the other stable particles in the standard model are neutrinos. And neutrinos are special. They're really, really ghostly. They're very, very low interaction rates, hard to see, and the Atlas detector is not one of these specialized neutrino detectors. Neutrinos or dark matter, anything that's very low interacting like that, will pass through our detector completely unseen. Right, so this is a sort of breakdown of these particle signatures. Do try and become very familiar with these. So this is the fact that we've got all these different types of particles and all of these different types of detector technologies and different layers of them enables us to both measure these particles and identify them, because you want to know what was produced in your collision. And we've got a sort of summary here. So electrons, as I said, there's a track in these trackers. So this first layer that we have is the tracker. The second layer is the electromagnetic calorimeter. The third layer is the hadronic calorimeter. And that last layer is the muon spectrometer. So a little bit drawn there. So we've got a track, and I've drawn it as bent because we've got a magnetic field, and it's pointing to a cluster in the ecal. And a photon, as I said, it will also be stopped and measured in the electromagnetic calorimetry there in the ecal, but there's no track because a photon is neutral. The muons are very penetrating. They're charged, so we'll have a track in the tracker, tiny, tiny little things in the calorimetry, and then it will leave a track in the muon spectrometer and leave our detector. Right, then we've got things like pions or protons here. They will leave a track if they're charged. A small shower in the ecal, but usually the large shower in the hcal as they're finally stopped. Neutrinos, absolutely nothing. I do want to point out a special case of pions here. The pi zeros versus the charged pions here. The charged pions I just went through, you have a track and your clusters in the calorimetry. Pi zeros decay very quickly and almost 100% to 2 photons. They actually sort of do it within the tracker. So they're neutral. You don't see them in the tracker. They're decaying to 2 photons, which are also neutral, so you don't see them in the tracker. So what you do see from pi zeros is, instead of just like a neutron, what you actually see is 2 very closely spaced photon showers in the ecal. So they're a bit of a special case. If there's a pi zero in the final state, just draw 2 little photons next to each other. Right, so we've done electrons, we've done muons. What about taus, the even heavier version? They actually decay really quickly. We don't directly detect taus in these kind of colliders. You will observe their decay products if it decays to electrons or muons or hadrons. You'll want to just draw their decay products and not the taus themselves. They will essentially decay within the beam pipe before it reaches any of our detector technology. Neutrinos, as I said, they're very special, they're very weakly interacting, and we do not detect them. Don't draw a dash line. Just draw absolutely nothing. You can always leave a note outside saying the neutrinos are not detected. Hadrons, we had a little word about. If they are charged, they'll leave a track and then calorimeter deposits. If they're neutral, just their calorimeter deposits. And then finally, I want to discuss quarks. When we make a quark anti-quark pair, for example, in our detectors, and they've got lots of momentum and they're flying away from each other, there's something very special about the strong force. That means they undergo something called hadronization, and they're each seen as a spray of hadrons, not a single quark. You can't have a single free quark, which we'll get to, but instead they're seen as these sprays of hadrons called jets. You can think about it as a sort of spray of water, for example, and that's exactly what it looks like in our detectors. We see lots and lots of tracks, lots and lots of showers in the calorimetry as well. Basically, these sprays of particles all very close to each other. They're messy, they're hard to reconstruct, and at something like the LHC, where there's lots of hadrons about, we see lots and lots of these. So there's our jets as well. I'm going to go through a couple of examples so you become more familiar with these. I think it's problem sheet 2 where you get to practice these a little more on your own. So I'm going to take a collider that came before the LHC, the Large Electron Positron Collider, LEP, where we were colliding, as the name suggests, electrons and positrons. And in this collision, for example, we're going to pretend we've made a Z and it decays back to an electron and positron. So that's our final state. So here we have an electron and a positron. I don't really care which is which, but the one thing we've got to do is make sure their tracks bend with opposite curvature. And we're going to try and balance the event here as well. So we're going to bend the tracks with opposite curvature, track for each, pointing to a nice shower in the calorimetry. It's really this simple. And then what if that Z decays to a couple of muons? So again, they're going to both leave tracks in our tracking system, bend them in with opposite curvature because they have opposite electric charge. We're going to give, um, they're going to leave tiny deposits in our calorimetry and then a track in the muon spectrometer. Okay, make it all the way through. The Zs could also decay to a couple of taus, and like I said, these taus decay very quickly before we detect them themselves, so we will see their decay products. So we're creating a tau plus and a tau minus. What do they do? Here we're told that the tau minus decays to an electron and a couple of neutrinos, so all we're interested in here is the electron, because the neutrinos we will not see. And then the tau plus decays to a muon and some neutrinos. So all we're interested in here is the muon. All we have to draw here is an electron and a muon with opposite charges. So we're going to see two tracks bending in opposite directions. The electron has a shower in the ecal and the muon goes all the way through. Finally, Z bosons could decay to a couple of quarks, and this is where we're going to get these sprays of particles called jets. Well, we've actually got a 3-jet event here. You'll see more examples of this. For example, one of these quarks could emit something called a gluon, which also produces a spray of hadrons. So we've got these 3 sprays of hadrons going through with lots of tracks, lots of clusters of energy in our 2 calorimetry systems as well. Very, very messy. We do like to measure our fundamental particles like electrons and muons with far higher accuracy than our jets. Right, a couple more examples here. Here we could have made a W plus and a W minus, which decay to an electron and a neutrino and a muon and a neutrino. So we're only interested in the electron and the muon because these are the ones that we can detect. And so we've got our muon here and our electron here. Opposite charge again here. We could have W plus W minus going to a couple of quarks and an electron. So each of these quarks is going to give us a spray of hadrons called a jet. So we've got 2 jets, and then we've got our electron here. And I've sort of imagined that our neutrino went this way and left absolutely nothing. So you can kind of see an imbalance in the momentum of this event. And each of these Ws could go to quarks, giving us a 4-jet event. Nice and messy there. Okay, so what we're going to do next is switch to an example. We're going to have a look at an E plus E minus collider with our typical cylindrical detector around it. And we're going to take an example where we've measured a positron and an electron. We're going to have a look at their cluster energies and their momentum energies and have a look at the invariant mass of the particle that produced it. So we're going to take the invariant mass of those 2 particles. Now, typically a question will ask you to draw a lowest order Feynman diagram for this, and I'll draw this for completeness now, but we're going to have a look at it in the coming lectures. And it also usually asks you to draw a detector signature, so we're going to have a practice with that, and then calculate the invariant mass of these 2 particles. And so let's do that in the examples. Right. So as a reminder, we've got an E plus E minus collider. Nice and clean, those things. And a typical cylindrical detector, which is the ones that I've been looking at today. So we detected a positron and we detected an electron. This positron had some energy, I'm going to call it E1. We measured this in our calorimeter at 44.7 GeV. And there was an uncertainty associated with that, 1.2 GeV, just simply because of the energy that we measured and the number of particles in the cluster. We also could measure its momentum in the tracking system, and we measured its absolute momentum to be 46 plus or minus 3.2 GeV. And the same with this electron here. We're going to call it E2 and P2. We could measure the energy in the calorimeter from that cluster, that shower that it left. And this one was 46 GeV, or 46 plus or minus 1.2 GeV. And its momentum was 49.5 plus or minus 3.5 GeV. So I'm showing you the uncertainties for a good reason. Because the energy of this electron, or this one, doesn't matter which one, is so high compared to its mass. Remember, it's only half an MeV. Uh, so it's got a 46 GeV in energy. We can treat it as roughly massless. We should expect the energy and the momentum measurements to be roughly equal. They're not, but they do agree within uncertainties here. So sometimes these uncertainties are quite nice to see because you can consider them and see that actually the energy and momentum measurements from those two different detector technologies are roughly the same. So we have these things called Feynman diagrams, which are not just pretty pictures, are actually depictions of calculations, which we'll get through. But they can also help us understand what's going on. So what happens when we collide an electron and a positron? Let's have our electron and positron here. They're not spatial diagrams, but time is going to go from left to right to show you what's happening. These two collide and annihilate. They can annihilate to either a photon or a Z boson. And then it produces our electron and positron again. So this is what's happening in our collision. There's a lot of information that's within these diagrams that will help you do calculations. For example, there's these wonderful arrows on lines, which we'll get to. And these vertices here denote fundamental forces. So this photon and this Z are basically mediating the electromagnetic or the weak force. We could also have an electron and the positron come in, and instead of annihilate, just exchange a photon or a boson, just bounce one off in between them. And we don't know, event by event, which one's happening, if we have an annihilation or if they're just bouncing, exchanging a photon and a Z between them. We have no idea on an event by event basis. So these are the kind of Feynman diagrams that you'll draw. We will have an entire lecture devoted to these, but just for completeness, they're here and it's nice to start introducing you to them now. Right, the next thing we want to do is to draw the detector signature, and I think hopefully I'm going to be saved by some automatic circles here. So this is going to be our beam pipe. I'm just going to try and color it in. This is going to be our tracker, our let's try and make things a bit bigger. That's going to be our beam pipe. Let's draw our tracker with a bit more space so that you can see it. Usually we do center them a little bit better. There's our, where's my one that I prepared earlier? There's our electromagnetic calorimeter. Here's our hadronic calorimeter. And here's our muon spectrometer. Okay, not too bad. Right. We know that we're detecting one electron and one positron. I'm going to try and draw these in blue so that you can see them. Well, we will see them as being basically emitted from this beam pipe. Our electron will curve in one direction, our positron will curve in the other direction. It doesn't matter which one you choose, just make sure all the positively charged particles curve in one direction and all the negatively charged particles curve in the other direction. So they're both charged, they've got their tracks bending in opposite directions, and then they're both stopped by the calorimeters, the electromagnetic calorimeter. And so you've got a little cluster of energy there, which you can just draw with a little, almost a little scribble there. I've tried to draw them as balanced because we do expect momentum conservation after all. And while our momentum measurements here are not exactly equal, they are roughly equal in terms of their roughly 10% uncertainties that we see there. All right, the last thing we need to do is have a look at the invariant mass of these electrons and positrons. Right, we know that to conserve momentum, our electron and positron are back to back. I'll just write that, conserve momentum. So that I'm going to choose, for example, P1 to be equal to minus 46 GeV and P2 to be equal to, what was it, plus 49.5 GeV. Okay. And so let's take the invariant mass. To do the invariant mass of our electron and positron squared, we need to add their energies, square it, and then subtract their momenta. There we go. That's simply all we're doing. And so this is the 44.7 plus our 40, well, what was it, 46. And then P1 plus P2, when you the difference between those was plus 3.5. All right, so then MEE becomes 90.6 GeV. And one thing that we can note there is that this is very close to 91.2 GeV, which is the mass of the Z boson. So this is one way that we try and sort of tag what two particles may have come from. If this invariant mass was close to 0, it would be more probable that it came from a photon. But since it's very close to the mass of the Z, it's quite probable that they came from a Z boson decay. There's one more example that I want to just go through with you, because we've had a look so far at colliding electrons and positrons, and we've mentioned the idea of colliding protons. So if we're colliding electrons and positrons here, we can take the invariant mass there, the center of mass energy, using the electron and positron energies and momentum. So that would just be simply E1 plus E2, i.e., if they're equal and opposite, 2 times the energy of the beam. Right, it becomes a little bit difficult when we're colliding protons like we do at the LHC because they are not fundamental point-like particles. They're actually, you can consider them sort of bags of quarks that we're actually colliding. And what actually happens is that a quark or the gluons holding them together are the ones that collide. And on an event by event basis, for each collision, we don't actually know what fraction of the proton's energy these quarks or these colliding gluons, whatever they are, actually held. We don't know the center of mass energy. We do for the electrons and positrons, they are fundamental particles, but for protons, we don't. All we know is that there's a sort of maximum if these these quarks were holding 100% of the momentum, but it can go anywhere between 0 and that. So let's have a look at that. Let's say that this quark here was carrying some fraction x1 of the proton's momentum, and that means that it's carrying some fraction x1 of the proton's energy. And the same here, we're going to call it x2 p2 and x2 e2. We don't know what this fraction is, x1 and x2. We sort of know it on a statistical basis, but not on an event by event basis. So let's calculate our center of mass energy now. It's x1 E1 plus x2 E2 all squared minus x1 P1 plus x2 P2. Right, I'm going to, we'll get sort of the masses of the quarks there squared, masses of 2, well, let's just call it 1 and let's not scribble that out. And the mass of quark 2 there. And then we'll get other terms like 2x1, x2, E1, E2 minus 2p, x1, x2, p1, p2. Now, the masses of quarks are absolutely tiny, so I'm just going to ignore those and take them down to 0. Since their energies are going to be much higher than their masses, we can treat this as ultra-relativistic. We're going to collide these head on. We're going to say that theta equals pi, so that these terms simply become 2x1, x2, e1, e2, 1 minus cosine theta. All right, so here we've approximated their energies as their momentum and their masses as 0. Okay, so theta is pi. We're colliding them head on. So this is 4x1, x2, e1, e2. Very simply. So what if our protons are equal enough, have equal energy, just like they do at the LHC? We're just going to say E equals E1 equals E2 so that they're equal. Then we have 4x1, x2, e squared. So that our center of mass energy is 2 times the square root of x1, x2, oh, sorry, e, 2e, there we go. Right, so our center of mass energy depends on what fraction of energy the quarks are actually carrying and the energy of our protons. And we don't know that on an event by event basis. We do know it over a sort of data set though. So we need to understand these fractions or how the momentum is distributed within the proton constituents to understand what spread of center of mass energies are getting. So we need to understand these, what we call these parton distribution functions. We can put our sort of x, our fraction of the, is it that way? Yeah, and we'll put, right, what we're going to do here is draw a graph of the probability that a particular proton constituent is going to carry x fraction of the momentum. So for example, our up quarks, what have we got in a proton? We've got up quarks, down quarks, and gluons holding them together. Our up quarks usually carry around a third. They average at about a third of the momentum. And our down quarks, there's fewer of them. I'm going to draw that in red. And they usually carry, on average, around a third as well. We also have gluons. I'm going to draw that in green. Oops. I'm going to draw that in green. And they usually have a smaller fraction of the proton's momentum. You don't have to know this, by the way, I'm just showing you. And then also there's these things called C quarks, where these gluons can produce quark-anti-quark pairs in and out of existence all the time. And we can even have things like strange quarks, not very many of them sort of existing in our protons, but sort of just popping in and out of existence from those gluon pair productions, which is really interesting. So these are called parton distribution functions. We had experiments at DAISY in Germany, the HERA experiment in particular, did a lot of electron proton collisions to try and understand the parton distribution functions within the proton. And we use that information at the LHC to try and understand our spread of center of mass energies that we're expecting. So this is the reduced center of mass that we get from colliding non-fundamental particles. It's a bit of a pain sometimes when you're trying to understand the total energy or momentum of the event, because you don't know what you started off with, whereas for fundamental particles you do. But we know that protons are really, really useful in getting our center of mass energies up really high without too much power loss um, from synchrotron radiation. So it, it's a bit of a give and take, and we take that sacrifice. So we had a look at this already, and so we come to the end of the lecture. So right, let's try and summarize what we've done. We've had a look at colliders, we've had a look at our detector technology as well. We had a look at the center of mass energy that we can calculate for fixed target experiments versus collider experiments. And we found that we would prefer collider experiments over fixed targets because we can achieve a much higher center of mass energy. We're not wasting energy of our collision in the momentum of our final state particles. We've seen that we prefer circular colliders over linear colliders because we can reuse our radio frequency accelerators again and again as they complete the circle again and again. But we need high power magnets to do that, of course, to bend our particles in a curved path. And we've seen that we prefer to collide high mass particles like protons now instead of electrons and positrons because we have less synchrotron radiation loss with a high mass particle. And then on the detector side, we basically encase our collision point with cylindrical detectors with different layers of them. Those first layers are trackers to detect the path of charged particles. We put them in a solenoid so that we can bend them and measure their momentum as well. And then we have layers of calorimetry to stop and measure the electrons and photons and all of the hadrons as well. And then finally, that layer of tracking system around there to detect the most penetrating particles, which are muons. And we had a look at the detector design, why we layer them in this way, and the particle signatures that we can get out of these that enable us to identify different particles from one another and also take accurate measurements. Right, so that's the end of this lecture. We will spend an hour next on the standard model, where we will be looking at all of the different ingredients of the standard model and also how we're going to approach things. I'll see you then.